Hello and welcome to today's lecture. Today we will talk about coloring maps. So remember, previously we talked about coloring graphs. And as one example, I gave you the example where you want to color a map, such as the world map behind me, where you want to color each country so that countries that have a border do not have the same color so that you can see the map easily. And the way that I gave to do this is that you draw a graph where each country is represented by a vertex, and then you use the notion of colorability of a graph. But this is kind of an abstraction of the map. It would be much more natural to look at an actual map, like an actual drawing where you have not just vertices and edges, but where you have regions like that somehow, and then you want to color them in different colors so that regions that are next to each other do not have the same color. So there is one way to do this using graph theory, since we do have such a notion of regions, namely the faces of a plane graph. So for us, roughly speaking, and I will make this precise in half a second, a map will just be a plane graph where we want to color the faces instead of the vertices. So what is actually a map then? Well, we're going to use graphs, as I said, but we don't want any graph. There are some things that you never find on the world map. So, for example, there are no bridges. Bridges are edges that if you remove them, the graph becomes disconnected. So if assume your graph looks like this, then and then this is I'm zooming on a section of a graph here. Then this doesn't really happen in the real world, because this would be the same country on both sides. So of course you wouldn't have such an edge between the country and itself. Also, you will not have degree 2 vertices. So what is a degree 2 vertex? A degree 2 vertex is a vertex that looks like that. So assume that you have something like this. Well, I mean, if here you have country A and here you have country B, then there is no meaning of this extra degree 2 vertex in the middle, because you might just as well remove it, right? It's still going to be the same thing that you're modeling, that the two regions share a border. So when we will look at our graph theoretical maps, it is reasonable to say that we don't look at just any plane graph, but plane graphs where bridges and degree 2 vertices don't exist. One way to deal with this is to define a map as a plane graph that is 3-edge connected. And remember, being 3-edge connected, meaning that there is no disconnecting set having 1 or 2 edges. So removing one edge will never disconnect the graph, and this corresponds to no bridges, and removing any 2 edges will not disconnect the graph. And this implies that there are no degree 2 vertices, because if you had a vertex of degree 2, then you can just remove the 2 edges connecting the vertex to everything else, and the graph will become disconnected. So this, of course, also implies that the graph is connected to begin with. So a map is a plane graph that is 3-edge connected, and the previous paragraph was a motivation why this is a reasonable definition of a map. So now that we know what a map is, namely a 3-edge connected plane graph, we can find the notion of a map being face colorable. So a map is said to be k-face colorable, or K colorable F for short, if its faces can be colored with K colors in such a way that no faces with a common edge have the same color. So, for example, the thing I want to do is something like that. So assume that this is my graph. Then if I color this edge red, I have to color this face red, I have to color this face blue. It is perfectly fine to color this face red. This is why edge is highlighted, because these two faces, yes, they meet at a vertex, but that is not interesting. We only require there to be an edge in common between two faces to forbid them to have the same color. Now, to avoid confusion, remember before we talked about colorability of vertices as if that was the only way to color graphs, but from now on we will call a graph K-vertex colorable if we're talking about coloring the vertices, or for short K-colorable V, so as not to confuse it with K-face colorable. And so we might wonder, how are these notions related? What is there for a relationship between face colorability and vertex colorability? Well, what construction exchanges faces and vertices, one might ask. So this is a question to which you know the answer because of duality. So remember, by construction of the geometric dual, you have faces and vertices corresponding to each other. So faces of the original graph correspond to vertices of the geometric dual and vice versa. And so we can state the theorem that if you have a simple plane graph G and you take its geometric dual, G star, then your original graph is K vertex colorable if and only if the dual graph is K face colorable. So let's look at an example. Let's look at our example here where the graph G is this black graph. So G is the one with these vertices and these edges. And I have prepared this so we can see that this graph G, when we color the vertices, it is 3 vertex colorable because you can color this vertex green, this vertex yellow, and these 2 vertices pink or purple because they have no edge in between. Now if we draw in red the dual graph, so we put 1 vertex in each face and we connect with 1 edge across each edge of G, we get the dual graph. And often when you draw the dual graph like this, it's going to be messy because of all the multiple edges and so on. So you can draw it by itself. So here I have drawn G star. And the color of the vertex that's inside each face, so each face of G star is going to have a vertex of G. We'll see why in a minute. And this color gives the appropriate color to the whole face. So we get a yellow face, 2 purple faces, and a green face. And notice that these purple faces, they have a vertex in common, but that's okay so long as they don't have an edge in common. Now, if you are careful, you will have noticed that I've only defined face colorability for maps. So how do I know that the dual of any random simple plane graph is a map? So what is a map? A map is a plane graph that is 3-edge connected. The dual is always a plane graph by construction. So it's the 3-edge connected part that we want to make sure. 3-edge connected means that it has no cut sets of size 1 or 2. But cut sets in the dual correspond to cycles in the original graph because of this cut set cycle duality. So we must show that our original graph has no cycles of length 1 or 2. But this is always the case because the graph is simple. Cycles of length 1 are loops and cycles of length 2 are multiple edges. So the dual will always be a map. So how do we prove this theorem in general? Well, the proof is quite short. because vertices of our graph correspond to faces of our dual graph. We used this when we proved that the dual of the dual is the graph itself. So not only do faces of G correspond to vertices of the dual, but vertices of G correspond to faces of the dual in such a way that two vertices by construction are adjacent in the original graph precisely if the faces of the dual share an edge. So this is why this theorem holds in general.